Okay, picture this. You're sitting in the driver's seat, you turn the key or hit that start button, put your foot down, and you just move. It feels incredibly simple, right? But beneath that hood is an absolute masterclass in engineering, this highly choreographed mechanical ballet. In this explainer, we're going to track the insanely complex journey of a single burst of energy, from its explosive birth inside the engine all the way down to the rubber actually meeting the road. So let's dive into this.
Here is the roadmap for our explainer today. First up, the beating heart, the engine cycle. Then, the blood and sweat of the car, cooling and lubrication. Next, the muscle regulator, our transmissions. Followed by the driveline, which act as the limbs. And finally, the magic of cornering with the differential.
All right, let's start right where all that power is born. Section 1, the beating heart, the four-stroke engine cycle. So inside the cylinder, power is generated in 4 very precise strokes, and a stroke is really just the full travel of the piston moving up or down. Step 1 is intake. The downward motion creates a partial vacuum, which literally pulls an air-fuel mixture into the cylinder. Step 2 is compression. The valve snaps shut and the piston pushes back up, tightly squeezing that mixture together. Then step 3 is combustion. A spark plug ignites that highly pressurized mixture, creating a literal explosion that forces the piston violently back down. The specific stroke right here, this is what actually produces the mechanical work to turn the crankshaft. And finally, step 4 is exhaust, where the piston pushes all those spent gases out. Intake, compression, combustion, exhaust, over and over, thousands of times a minute.
Now here's a stat that is truly staggering. 25%. The internal combustion engine is technically a heat engine, but only about a quarter of the heat it produces is actually converted into useful power to move your car. Which obviously begs a massive question, right? What in the world happens to the remaining 75%? Well, a massive chunk of it just goes right out the tailpipe, but the rest is absorbed directly by the engine itself.
And if we don't manage all that wasted heat, the engine will literally destroy itself in minutes. That brings us to Section 2, blood and sweat, the cooling and lubrication systems.
Without a cooling system, the oil would break down, pistons would expand and seize, and the engine would stop dead. It's game over. The cooling system basically has 4 primary jobs. Yes, obviously, it removes excess heat, but it also maintains a totally constant operating temperature. It actually works to warm up a cold engine as fast as possible. And, as a really nice bonus for us during the winter, it provides the heat for the passenger cabin.
In a standard liquid-cooled system, you've got a water pump forcing coolant through these intricate little jackets and passages inside the engine block. And it relies on this beautifully simple concept called thermosiphon action. As the coolant heats up around the cylinders, it expands, it becomes less dense, and it naturally rises up to the top of the radiator. As the radiator cools that liquid with airflow from outside, the coolant becomes heavier and sinks back to the bottom. This creates a natural, continuous circulation loop that perfectly assists the water pump. It is an incredibly elegant way to keep the whole block from melting down.
Now, working right alongside the cooling system is the lubrication system. In a standard force-fed setup, an oil pump forces oil from the pan up through intricately drilled passages directly into the main bearings and connecting rods. But the oil doesn't just reduce friction. It actually squirts out to coat the cylinder walls, carrying away intense heat and absorbing the violent shocks of combustion to quiet the engine down. You can really think of it as the immune system of your car.
Okay, so we've got a spinning, cooled, and lubricated engine generating power. But if we connected that power straight to the wheels, you'd stall immediately at a stoplight or top out at maybe 10 miles per hour. Enter Section 3, transmissions, the muscle regulator. If you've ever driven a manual transmission, you are relying heavily on a brilliant little component called a synchronizer. See, when you shift gears, the engine output shaft and the new gear you want are spinning at entirely different speeds. You can't just jam them together without a horrific grinding sound. The synchronizer uses a blocker wing pushed against a cone on the gear, using pure friction to equalize those shaft speeds. Once the speeds match up perfectly, the keys and notches align, allowing the slider teeth to lock the gear to the output shaft flawlessly.
But what if you don't drive a stick shift? Well, the landscape of modern automatics is wonderfully diverse. Take the dual-clutch transmission, or DCT. It literally has 2 clutches, one for odd gears, one for even, riding on concentric shafts. It pre-selects the next gear for near-instant swaps. Then there's the classic torque converter automatic. This uses planetary gears and a fluid coupling to multiply torque right at launch before locking up. And then there's the CVT, or continuously variable transmission. Instead of fixed gears, it uses variable pulleys in a belt or chain to constantly, seamlessly adjust the ratio.
And for sure, we can't forget hybrids. A hybrid transmission has to perform a really complex balancing act. It's managing traditional combustion power alongside an electric motor. Because electric motors deliver full torque instantly from a dead stop, the transmission uses the electric motor to assist the gas engine during hard acceleration. And it's so smart that it acts backwards during braking, turning the motor into a generator to capture kinetic energy and recharge the battery.
So we have power, and it's been regulated into usable speeds by the transmission. Now it actually needs to travel down the length of the car. Welcome to Section 4, the driveline.
The absolute star of the driveline show is the drive shaft. It looks surprisingly simple, just a hollow metal tube spanning the bottom of the car. But because it can spin at full engine speed, it has to be perfectly, and I mean perfectly balanced at the factory. If it isn't, the vibration would shake the entire car apart. But here is the major engineering problem. A car isn't rigid. As you drive over bumps, the rear axle assembly moves up and down on its suspension, which is constantly changing the physical distance between the transmission and the rear wheels.
So, how do you connect two things with a solid metal pole when the distance between them is constantly changing? The answer is the slip yoke. It's a splined connection at the front of the drive shaft that provides this clever telescopic action. As the rear axle bounces over potholes, the slip yoke just slides horizontally in and out of the transmission output shaft, all while continuing to smoothly transmit that turning power.
Now, at the ends of the drive shaft are joints that allow the whole thing to flex. Traditional universal joints, or U-joints, are great for rear-wheel drive setups where the angles are pretty small. But if your car is front-wheel drive, the front wheels have to cramp up to 30 degrees just to steer the vehicle. If you used a standard U-joint bear, the varying geometry would cause intense speed pulsations. You'd get incredibly hard steering and tear up your tires in no time. That's exactly why front-wheel drive relies on constant velocity, or CV joints, which completely eliminate those pulsations, transferring perfectly smooth power even while you're cranking the wheel into a tight turn.
All right, that power has finally reached the axle. But there is one last, massive mechanical hurdle to solve before we can actually drive normally. Finally, Section 5, cornering and the differential.
Think about a marching band turning a sharp corner. The people on the inside of the curve pretty much have to march in place, right? While the people on the outside literally have to run just to keep the line straight. A car is exactly the same. When you take a turn, the inner drive wheel has to spin slower because it's traveling a shorter distance, while the outer wheel must spin much faster. If your two wheels were joined by a solid, unbroken metal bar, they would physically have to hop and slip across the pavement every time you turn the steering wheel.
The ingenious solution to this problem is the differential. Here's how this absolute masterclass in mechanics works. Power from the drive shaft comes in through a pinion gear, which rotates a much larger ring gear. Inside that ring gear is a spider gear mechanism. When you're driving perfectly straight down the highway, the entire assembly just rotates as one solid unit. But the very second you turn a corner, the unequal resistance from the inner and outer tires causes the side gear pinions to literally walk around the side gears. This is the mechanical magic that allows the outer axle to rotate faster than the inner one, keeping both wheels fully powered without a single bit of tire slip.
And for high-performance situations, you might run into what's called a clutch pack limited slip differential. Under high torque, the rotation pushes the axle side gears out against a series of clutch discs, essentially locking the wheels together for maximum traction off the line. But when you back off the power to take a normal corner, a pinion shaft slides down a clever V-shaped ramp. This releases the pressure on the clutch pack, allowing it to deliberately slip just enough to let the wheels spin independently through the turn. It's brilliant.
From creating a miniature explosion, to cooling the molten heat, to equalizing shaft speeds, telescoping metal limbs, and finally letting wheels spin at entirely different speeds on a curve. It all happens in fractions of a second without you ever having to even think about it. So, the next time you turn that key and put your foot down, take a moment to appreciate the thousands of perfectly synchronized mechanical decisions happening right beneath your feet. I highly encourage you to keep exploring these systems. It truly changes how you view your everyday commute. Thanks for learning with me on this explainer. See you next time.